Right, we'll talk about the chain rule today, which is arguably, I think, the most important of all differentiation rules we'll learn in this class, which is why it comes last. Okay. The idea is to be able to, or I found a typo there. So this is f of x equal to square root of x squared plus 1. If you look at this function here, there's just no way how we could use one of the rules that we've already found or used to differentiate that. This is not just a power function. Indeed, there is a power function in there, and we call it f, little f of u equals u to the 1/2 power, right? It's written as a square root, but it's the same. So there is a power function there, and there is another function there that's a polynomial, x squared plus 1 inside little f. So we kind of have an issue because there's two functions being applied to x, both of which we know how to derive, but the whole composition we don't know how to derive. And that's the issue. Big F is the composition, F composed G, right? Remember composition. Let me write in blue so that you remember that's the composition. From Math 141, right? Pre-calculus 1. So there is a composition that we don't know how to derive, but we know how to derive both little f and little g, but we don't know how to derive big F. So the chain rule is going to let us do that. It's going to let us find the derivative of a composition given, both derivatives of little f and little g. So this is what we call the chain rule. And the word chain comes from the fact that we're applying g and then applying f and then h, and then whatever comes next, we're applying one in succession of the other, one function in succession of the other. So that's why chain rule. Super cool and easy to remember. This is what the chain rule tells us. I'm not going to walk you through the derivative, through how to prove this. It takes some time to prove it. You got to go through the epsilons and deltas or the delta x's. I'm not going to show you how to prove this. It's very easy to remember. Why? Because if you use Leibniz rule, you can sort of look at the right hand side of this equation that I just boxed and cross the du's, right? Note that in the previous slide, the function f, right, I'm writing it in terms of u as a function of u and not of x, and that's because I have to derive it with respect to what it is, right? To the variable it uses and not to the variable x anymore. So that's why we have another du here. And that's why it's super cool and easy to remember about the chain rule. Okay, just take a look at this. Try and understand what's going on. You can also write it using Newton's notation, or prime notation sometimes it's called, where you have this, f prime of g of x times g prime of x. So this one, let me box them both and add my already famous little exclamation points so you know these are things you have to remember. They are very, very important. I find the second boxed equation a lot easier in Leibniz notation, a lot easier to remember, but the first one sometimes it's useful as well, and I'll use it. So you have to be able to recognize it, that it's the same thing. Right? In this case, just in case you were wondering, g of x equals u, right, is what we're calling it. And then that's where it comes from. We'll do a couple of examples, and it's going to make a lot more sense to you. It's just showing the same thing to you again. And while, like I was saying before, you can do this, you don't think of it as quotients. That's not, these two things are not fractions, they're just derivatives, but it kind of reminds us of it, so we're allowed to think of it that way, at least to memorize the formula for the chain rule. So let's go ahead and actually solve this problem. Okay, let's think about it. So note that, let me break this apart into two halves here. F of x, like I was saying before, this is f circle g of x, right? F composite g, where and I'll call g of x is the first function that I apply, is x squared plus 1. And then f of u, I'll use a different variable, is square root of u, right? It's the same as u to the 1/2 power, because then I'm able to use the power rule with it. So I can go to the other side and say that by the chain rule, capital C just this time around, f prime so let me actually just write the formula. It's going to be f prime of g of x times g prime of x, and then let me derive on the left side. So it's going to be g prime of x, very easy to do, I just use the power rule here, and the derivative of 1 is 0, so that's 2x, while f prime of u, so I'm now deriving f with respect to u, which is its variable, so I bring the 1/2 down, right, and the u loses 1 in its power, so I do 1/2 minus 1, that's minus 1/2, right? Just remember the power rule, and these are the two things that I have to use. So back to the right side, this is f prime of g of x, so I go on f prime, which is what I just found, and I plug in g of x into u, so that's going to be 1/2 g of x to the minus 1/2, right? So I'm plugging in g of x into u, and that's why I said back there, right, that g of x equal u. So let me just circle that here. So that it's clear for everybody. And then g prime of x I just found, so that will be 2x, right? So then I can continue, and I'll be able to find my derivatives. So g of x will be 2x, no, sorry, x squared plus 1 to the minus 1/2 times 2x, and these 2's, they cancel out. So then I get x times x squared plus 1 to the minus 1/2, and that's the same as x over the square root of x squared plus 1. This minus 1/2 power becomes a square root in the denominator because of the negative sign. So that's the derivative I was looking for. Looks pretty nice. Usually I don't like square roots in the denominator, but comparing to what I started with, which was nothing, I had no idea of what that derivative was. That's a huge advancement for us. That's huge progress, right? Just using the definition of derivative would have been such a hustle for us. It would have been a lot more difficult than this, of course. So like I said before, there is a way to do this, and that's the goal. The goal of this chapter is to avoid work, or avoid a lot of work, and make it practical. So let's do another example, because maybe that allows us to be a little bit more practical. So I'll use the derivative, the Leibniz notation this time, so maybe that helps you. So what I'll do is this. I'll say just so you're aware that we're using Leibniz notation, I'll call u equals x cubed minus 1, right? Which is the inside thing, right? And then that gives me y equal to y equal to u to the 100th power, right? So I go by the chain rule, dy dx is dy du times du dx, and that's that. There's that nice little canceling looking expression. I won't cancel it out, right? This is not really a fraction. This is just something that reminds me of fraction multiplication. So just turns out that it works There's very heavy, deep mathematical theory of differential forms that explains why it works. But for now, just think of it as just something that it reminds you of. So dy dx is what I'm looking for, this here. Dy du is a lot easier because look at the left side again, right? Dy du, I'm just deriving this. So I get 100 times u to the 99th power. That's the power rule. And then du dx, I'm deriving this. So that's easy as well. That's just 3x squared. So I just go back there and I go 100 u to the 99th power times 3x squared. However, I don't want to have the cu here, so I go back to this initial assessment that I made, which has to do with, it's even in the same color from what I did before, right? The fact that g of x equals u, right? U is the function that is applied first to x. So that's 100 times x cubed minus 1 to the 99th power times 3x squared. I don't think I can do much better than that. Maybe I can put this 3 and this 100 together, so I'll do that. So I'll do 300x squared times x cubed minus 1 to the 99th power. And I think that's as far as I can go. Okay? So maybe it doesn't look great, but it is what it is. It is the solution to the problem. Okay, that's the derivative. If I were looking for, say, y prime of 0, I could easily find it by just plugging in 0 there, right? Y prime of 1, I could easily find it as well. So the alternative would be to actually start this and FOIL this out, but the power of 100 just makes it so impractical to FOIL it that the chain rule is basically the only way how I could solve this problem. Okay, just think about it again, look at it. So far we're only looking at the chain rule and how to use it, not really prove it, but like I said before, there is a proof for it and you're invited to read it and we can talk about it if you're interested. There is if you're going to pure math or a more theoretically heavy course, you can take a course called Real Analysis, which is where all of these properties are actually proved in a lot more detail than Stewart's book even talks about. But anyway, let's see another cool application of the chain rule, which is, so far we've only been able to find that e to the x prime is e to the x. So we've only been able to find that, but what if you have a different exponent with a different base, right? What if you have this, right? What do I do with that? That's the whole thing. So how do I derive, say, 2 to the x, right? If the base is not e, and that's the big problem. So what I do with it is I say b to the x is the same as e to the ln of b to the x, right? And that's what it's doing here, which is this. And now I have two functions. I have, I call u equal to, let me do it in blue like I was doing before, u equal to ln of b x. This is a constant because b is a constant. Right, so x is the only variable, the only unknown, and then y equal to e to the u. So then you use the chain rule with that, right? So dy dx is dy du times du dx, so that equal to dy du is derivative of this with respect to u, so just e to the u, times du dx is derivative of this with respect to x, so just ln b. Right. So e to the u is back to, remember what u was, right? U was ln bx, which is just b to the x times ln b. So that's what we end up with. And that's what will be boxed in here. So that's important. You either memorize this, Sometimes when I'm working on calculus for a long time, I do remember it from the top of my head, but sometimes I have to do this math all the time when I forget it. So one of the two, either remember it or you should be able to recall this formula using the chain rule. Okay? All right. So let's see at this particular example. If you're deriving 2 to the x, which is what I talked about before, this is just 2 to the x times the ln of 2. So it's not just the derivative of e to the x was just e to the x, but now if you're deriving e to the x, or 2 to the x, you're taking 2 to the x, but then you have this extra term, right, which has to do with the ln of 2. Remember, the ln of e is just 1, so this extra term is just 1 when the base is e, right? And this is just the final observation to tell you what happens when you add more links, right? If you have, say, F, G, and H, one in succession of the other. Let's say you're trying to do big F this time is, I'll do it in blue, big F equal to, so let's say first you're applying G, and then you apply F, and then you apply H. Okay. Then if you were to use, let me see what's going on here. So actually H is last in their notation, so it's F, G, H. So see, H is X, so it's the last one. But it's still as a function of T, right? So there's a T there. So in reality, this big F is a big F of T. Right? So you're saying H of T is X, G of X is U, just like before, and F of U is Y. So then instead of just going this part, having this part here, you have this extra part because now X is also a function, right? So you got to use the chain rule twice to get these 3 terms. So that's why chain, right? Like I was saying before, you can do it in succession. We're going to see examples of that, of more than one composition. We're going to have to become very proficient with that. But so far, this is a good introduction to the chain rule. Thank you for watching this. Let's keep studying. You're going to do okay as long as you understand and take your time to read this over again and ask questions.